All right, here we have a very easy page of notes because we're not introducing any new equations. You don't want to think of this page of notes as new equations, just taking equations we now know, and we're going to manipulate them a little bit to generate an equation, but we should not think of anything on this page as really being new. So we're starting with our charge on the capacitor as a function of time as the capacitor begins to charge up to a maximum value, Q max, based on the bracketed term. So charge on the capacitor at any time t equals Q max, bracketed term, 1 minus e to the minus t on RC. And hopefully I have convinced you to just memorize that and to know that that bracketed term goes between 0 and 1. Well, we started out with capacitance by saying that the charge on the capacitor, looking at Michael Faraday's work, equals CV. So the voltage on the capacitor follows the charge. And if we rearrange this, we get V equals Q divided by C. So all we are doing is simple substitution. We are taking our Q here, plugging it in for the Q, and we get our expression for voltage. So, and just like we saw on our last page of notes graphically, the voltage follows the charge based on the bracketed term being identical, 1 minus e to the minus t on RC, and of course that goes between 0 and 1. Now we also know that the energy stored in the capacitor, so we derived this earlier in the course, 1/2 C voltage across the capacitor squared. So all we are doing is again a substitution of the voltage across the capacitor into this equation to generate our end result for what we are looking at, the energy stored in the capacitor here. So we have the energy at any given point in time that a capacitor is storing is based on a maximum value of 1/2 CV squared, where the V is the battery voltage, and our bracketed term now has this squared in it. So it's our normal bracketed term, but it's squared. It still will go between 0 and 1, where, of course, there's no energy stored in the capacitor at time t equals 0 because it's just beginning to charge. That first Q isn't there yet. It'll have a maximum value of 1/2 CV squared at time t equals infinity, where this represents fully charged. So again, nothing new on this page. I don't advise you to memorize this as a separate equation. We do need to know the basic equations, 1/2 CV squared. We need to know Q equals CV, V equals Q on C, and we memorize this first equation. But now we have an expression for the energy as a function of time. So easy page of notes, and we are ready to go onward.